So last time we had talked about solving systems of equations and inequalities by graphing. And I asked you to work on 1 through 8 on the problem set. Let's start here with an opportunity to ask questions about any of that, 1 through 8. Reese? I'm sorry, Grace.
It's okay. I knew what you meant.
The hand, I couldn't tell whose hand it was. That's the excuse I'm going to go with.
Okay, yeah.
Okay. Not that I just made a mistake. You said 8?
Yeah.
All right. So the system here for 8 is this one. So I'm going to start by rearranging these bottom two inequalities so that they're in like slope-intercept form. The first one I don't have to do anything for because the y is already by itself. So far, so good?
Yeah.
Okay. So again, I'm going to just kind of pretend that these are equalities so I can find points on the lines. So I'm just going to kind of pretend they're equations. Yeah.
The second one, it's supposed to be x plus 3y.
Oh, cool. So 3y, 3y. That's going to change. Well, yeah. All right. Less than negative 1/3 x plus 5/3. Did you not just now? Yuck. Did you not like the fractions there?
Yeah, I don't know.
It's all right. So I'm going to be a little bit careful here. So I'm going to pick x to be 2. So when I plug that in, negative 2/3 plus 5/3 just gives me 3/3. And then maybe I'll pick I don't know, let's say negative 5, because that'll give me negative 5/3 plus 5/3. That gives me 0. That way I can avoid having to graph any fractions, because that's just kind of a hassle, you know? Not that it's a big deal, but I don't want to have to do it if I can just be clever and pick, you know, pick around having to do that. Okay. So I've gone ahead and I've picked some points on each of the lines. Again, it doesn't really matter which points I find. I just need 2 points on the line. You know what I'm saying?
So for the first one, where it's just x, I mean y is x.
Mm-hmm. Whatever x is, y is, right? So you just pick any values. I just picked 0 and 2 for x. It means y is the same thing. So this one I'm going to draw in red. There I'm going to draw in blue. I'll draw this one in green. So I have 0, 0, and then 2, 2. And this was a or equal to inequality, so I'm going to draw it with a solid line. And because it's a greater than, I'm going to be shading above, so I'm just going to draw a little arrow reminding myself which way I'm going to do the shading, because I don't really want to draw one shaded region where everything is overlapping, because that's just kind of makes life easier. Let's see, so my next one, I'm going to graph the point 2, 1, and the point 0, negative 5. And this one is a strict less than. So this one gets a dashed line. I tried to draw that straight. It doesn't look very straight, but we're going to go with it. If I had a ruler that I could use on my screen, that would help, but you know, that's life sometimes. And then we have 0, negative 3, and then negative 2, negative 1. And this was an or equal to is inequality, so I'm going to draw that with a straight or a solid line. Oops, I guess we forgot to shade on the blue one. So the blue one's a less than or equal to, so we're shading down. And the green one's a greater than, so we're shading up. So the piece that I think I'm looking for seems to be this little area right in there. That's below the blue line, above the red line, and also above the green line. Does that feel okay? Others, anybody else? Eric. Sure.
So on the second line, is it the sign to be switched because you divided by 3?
You only flip the inequality if you divide by a negative value. So since I divided by a positive, it's okay. Nothing had to change. Yeah, no problem. Again, good clarification. You're right on that sometimes that switches, and sometimes it switches with division, but you need multiplication or division with a negative to make the inequality symbol flip directions. Any last call on questions? Yeah, Joe?
Can we do one more of like the same problem? Is that cool?
Sure.
Similar problem. Can you do like number 5 on solve the system of inequalities?
Yeah, sure. Okay. So again, going to start by putting these in slope-intercept form. So I'll subtract 4x from both sides. And then the other one, I'm going to add x to both sides. Then the top one will divide by negative 4. So here the inequality symbol is going to switch directions because we divided by a negative. And on the bottom one, we're going to divide by a positive 2. So there the inequality symbol is going to stay the same direction. So now I'm going to find 2 points that lay on the lines. So I'm going to just kind of pretend these are equations and not inequalities for a minute. So 0 and 4, and then like negative 4 and 0. Seem like good ones. So 0 and negative 2, and then 4 and 0. Now we'll draw our graph. Everybody's okay with how I'm generating the points, right? Do I need to go further into that? That's like an algebra or pre-algebra skill doing that, but if we needed to review it, I'm happy to do that, but let me know. I assume that it's okay. That's why I just do it real quick. If it's not, holler at me and we can review it. Okay, if you change your mind, let me know. Okay. So I guess the first line we'll draw in red, and the second one I'll draw in blue. So 0, 4, and then -4, 0. And because that was a or equal to inequality, I'm going to use the solid line. And because it was a less than, I know I'm going to be shading below. I'm not going to do the shading right now. I'm just going to put an arrow reminding myself what side I'm shading on. The next one, 0, -2, and then 4, 0. Again, this is a solid line. So I got that going way over there, so I guess I need to make this line a little bit longer. There we go. And the blue line we are shading above because it's a greater than or equal to. So the area that I'm interested in is this section here in between the two. Does that feel okay?
Perfect. Thank you.
Yep, no problem. Again, to make sure that you have the correct shaded region, an easy check you can do is just pick some point inside that shaded region, like maybe 0, 0, and just make sure that satisfies both inequalities. So for example, if I take the first one, if I plug 0, 0 in for that, checks out. If I take the second one, and I plug 0, 0 in for that. Oh, wrong directions. Which makes a lot of sense because 0 isn't greater than 4. And I get -2 here is less than 0. So that's feels pretty good that that's the correct answer there, right? Do we get what I did for my check? Again, you don't have to do that, but if you're in a test or whatever, and you're like, boy, did I get the right overlap? You just pick a point in the intersection, in the shaded area, and plug it into both inequalities and make sure that it satisfies both inequalities. And you probably got it. Is it possible that there's still a mistake there? Sure, because you can't check every point, but you probably got the right area. And what might be even smarter is instead of using the slope-intercept versions that we made, is to go back and use the original one. So if you made an algebra mistake in generating your slope-intercept one, like you forgot to flip in an inequality symbol or something, that won't get you. So probably that's the smarter thing to do if you're being really cautious about your checking. Does that make sense, guys? All right, well, let's kind of continue forward. So at this point, we've talked about solving systems of equations and systems of inequalities graphically. Today, we're going to continue on and talk about solving systems of equations algebraically. Because as nice as these graphical methods are, they're kind of tedious. And if you don't have, a really nice, accurate graph, or if you don't have like an electronic means of doing the graphing, like a graphing calculator, they can be kind of, unreliable. So we prefer to use some algebraic methods where like the neatness of your picture doesn't impact the quality of the answer you can get. And even if you are being like super neat, if you have an answer that's like goes out to 2 decimal places, good Lord, that's going to be really a troublesome graph to create. If your answer is really like, 3.17 comma 4.26 or something. Ay caramba, that seems like a hassle if you're going to try to graph that to get it accurate enough to read to the hundredths place. Where algebraically, it doesn't really make much of a difference for us. So we're going to talk about 2 methods to do this. The first method is called substitution. And these are the same 2 methods that we used in our algebra course last year. So the idea with substitution is we're going to choose one of the equations, and in that equation get one of the variables by itself. After we do that, we're going to use that first equation and substitute I'll just say it into the second equation. Well, maybe I should say other. And then we solve this new equation. And then the last step would then be to back substitute and solve the other variable. So let's just kind of run through this process with a couple of examples. Okay, let's say our system is 2x plus 5y equals -5. And our other equation is x plus 3y equals 3. So I can choose either equation to use in my first step, and I can choose to solve for either variable in that equation that I've chosen. If I look at this, though, there's one here that screams out as the easiest to do. Can anybody take a look at the 2 equations and the 2 variables in the 2 equations and figure out what's going to be the easiest thing to get by itself? In which equation? In the second equation. Good. So the x in the second equation is going to be what I'm going to get by itself. And the reason I would do that is because, well, the coefficient on x is 1, so I don't have to divide, so there's no chance of generating any fractions. Not that that's a big deal, but if I don't have to deal with any fractions, I mean, I'd prefer not to. So in step 1, I've chosen equation 2, and I've gotten the x by itself just by subtracting 3y from both sides. In step 2, what I'm going to do is, since I know that x is equal to 3 or -3y plus 3, I'm going to plug that into the first equation. So I'm going to take my first equation, and in place of x, I'm going to be writing what x is equal to, which would be negative 3y plus 3. Is that okay with everybody? Notice when I do that in equation 2, the only variable left is a y. So that, since there's just one variable, I can solve. So in step 3, I'm going to just distribute that 2 through my parenthesis. And then we'll combine like terms. So negative 6y and positive 5y just becomes negative 1y. And then I'll subtract 6 from both sides and divide by negative 1 to get y equals 11. And now that I have that one variable, I can plug that value for y back into any of my previous equations that have an x and a y to solve for x. Specifically, what I would choose to do is I would plug it in here, because in this equation, the x is already solved, it's already by itself, so it just saves me a little bit of algebra. So when I plug 11 in for y, I get negative 3 times 11 plus 3, which when I simplify that down gets me negative 30. So taking these two together, we'd say our answer is x, comma, y. If I wanted to check this, what could I do? I just go back to the original equation and plug in negative 30 for x and positive 11 for y and make sure that both equations are satisfied. Everybody okay there? Let's look at what'll happen when we're doing these substitutions and say we get one of the other solution possibilities, like no solution or infinitely many solutions. Let's see what that looks like. Because again, it's not always like super duper obvious what that would mean. So here's another example. I look at this, and it doesn't seem like any variable in any equation is going to be particularly much easier than any other to solve for, right? Since all of them I'm going to have to divide and be left with a fractional coefficient somewhere. So I would just say I'm going to just get the x by itself from equation 1. So I'll add the 3y over and then divide by the 2. Now, I did notice that this is probably going to be the easiest one to do, since at least my denominator in all my fractions here is an even number, and the coefficients in my other equation are even. So at least when I substitute this back in, all the fractions will go away, but not too big of a deal there. So now we'll do our substitution. So we're going to substitute our x from the first equation into the x in our second equation. So in place of x, I'm going to write 3 over 2y plus 7 over 2. But all the rest of the parts of equation 2 remain exactly the same. I'll go ahead and distribute things through. So negative 4 times 3 is negative 12, and then when I divide by 2, I get negative 6. And negative 4 times 7 is negative 28, and then when I divide by 2, I get negative 14. And now when I combine like terms, negative 6y and positive 6y just kind of cancel out. So I'm just left with 14 equals 10, or negative 14 equals 10. Is that right? Is negative 14 equal to 10? No, that's a false statement, right? So what that tells me then, if I get a false statement like this, is that there is no solution. If I have no variables left, and I'm left with something like that, it just means there's no solution. What does an infinitely many solution situation look like? It's just if I have a true statement. So if I got like 14 equals 4, or negative 14 equals negative 14, that would be what my infinitely many solution situation looks like. So again, all the variables just cancel out when I do my substitution. And I'm left with something that's true. 5 equals 5, or negative 14 equals negative 14, or 8 equals 8, or 0 equals 0, or whatever. Does that feel okay? So easy to tell them apart, but it's worth pointing out that, when all the variables cancel out like that, come on, there you go. That's what's going on. Does everybody feel okay on that? All right. Any questions about substitution here before we move forward? Okay. Our second technique is called elimination. This is the one that Mr. Kulik actually prefers to substitution. More often than not, he finds this one a little bit easier. Mostly because you don't run into a lot of fractions when having to do this. So the first step is going to identify a variable to eliminate. Then we're going to multiply one or both of the equations by a number, or maybe numbers, right? Well, you have to use two different numbers if you're multiplying both equations, so that the coefficients of one of the variables are opposite. So, we're looking for something like one of them's 2x and the other's negative 2x or whatever. That's what you're trying to create. Then we're going to add the two equations, creating a new equation with only one variable. Let's not say that, because you could get no variables. Eliminating a variable. That doesn't preclude the possibility of both of them eliminating. That's good. And then we're going to solve this new equation. And then we are going to back substitute and solve. So let's say we have the system 3x minus 7y equals 10, and the equation 6x minus 8y equals 8. For notational purposes, I'm going to refer to the first one as equation A, and the second one as equation B. So what I'm going to do is I want to either multiply one of the equations or both of the equations by some numbers so that when I add the two equations together, one of the variables will cancel out. So if I say, okay, maybe I want to try to eliminate the x's. I notice that if I multiplied equation A by -2, then the coefficients on the x's would be opposite. So one thing I could do is I could do -2 times equation A and then add it to equation B. Or perhaps instead I wanted to do the y's. That would be okay also. Although this one's a little bit trickier. Notice that there's no common, the greatest common factor between 7 and 8 is just 56. So I could do -8 times equation A plus 7 times equation B. Or I could have made use +8 and -7. That would have been okay also. So any of these are like acceptable ways to do the elimination. Of these three options, which one do you guys want to do? I would do the first one because, it's the least amount of stuff that I have to do, right? So -2a would be -6x plus 14y equals -20. So notice here, maybe I'll do this just to kind of illustrate what I was doing here. Notice when I did that, I multiplied the -2 by every coefficient in equation A. Everybody see that? Now equation B, we didn't have to do anything to. So I'm just going to write equation B right underneath. I'm going to write my little addition symbol, and then I'm just going to add down. And as long as everything is lined up, we're good, right? So negative 6x plus 6x just gives me 0. I'm not going to bother to write anything. Positive 14y plus negative 8y gives me 6y. And then negative 20 plus 8 gives me negative 12. That's my new equation. So to solve for that, we'll just divide by 6 to get y equals negative 2. Everybody's okay there? To get my other variable, to get my x, I'm going to go ahead and plug in negative 2 back into either the equation A or equation B. It doesn't really matter. I'm going to use equation A because the coefficients are smaller. So I'm just going to say we're plugging y equals negative 2 into equation A. So that's just a little notation I'm going to use to remind myself what I did here. Does that all look okay? And now I'm just going to solve for x. So negative 7 times negative 2 is positive 14. Subtract that 14 from both sides, and then divide both sides by 3. So when I put those two together, my solution would be negative 4/3 comma negative 2. What do you guys think so far? Is this okay?
It's not bad. It's easier than the last chapter.
Yeah, for sure. For sure. Let's do another story problem example, right? We did a story problem example last time that was probably felt rather challenging. But let's do another one to kind of practice that. Again, the trickiest part for these is often getting the equation written correct, or the equations written correctly. It's just the decoding piece. So to raise money for a football uniforms, you decide to sell t-shirts. Short sleeve shirts cost $5. And can be sold for $8. Long sleeve shirts cost $7. And can be sold for $12. at the end of the fundraiser, you've spent $2,500 on t-shirts, and sold all of your t-shirts for $4,200. The question is, how many short sleeve t-shirts did you sell? Ooh, ooh. So in this question, what are the variables? What are the things that we're looking to find? Okay, so I'm going to use S to be the number of short sleeve t-shirts. Okay. And while it doesn't ask this directly in the question, what is the other variable going to have to be? No, we know the price. The number of long sleeve t-shirts, because we know the total costs and the total profit that we made was a result of sales of both of those. So we're going to need to know the number of long sleeve t-shirt also. Everybody okay with that? So we have our two variables. Now we're going to need to write two equations. So what is one of the equations going to have to represent?
One have to represent short sleeve, one have to represent long sleeve.
Well, if we're solving a system, which is probably a fair thing to assume from this chapter, both equations are going to have the variable S and L in them, right? So let's look at the other pieces of information that we're given here. Okay, we know how much it cost for a shirt of each type and how much we sold a shirt of each type for. And then we know how much we spent in total and how much we sold the shirts for in total. So when I read this sentence is going to be the one that's going to be kind of the key to me for how I'm going to set up, or what two equations I'm going to try to write. I'm going to try to write one equation for the total costs and one for like the total revenues. The money I spent and the money that I brought in. Does that make sense to you guys? Again, usually when you have like total number like that is usually going to be an indicator that that's one of the equations needs to represent something like that. Okay. So my equation A and my equation B, one equation is going to equal the total cost for the t-shirts, and one is going to be the total revenue for the t-shirts. How do I get the total cost? Let's say hypothetically I bought 10 short sleeve t-shirts and 8 long sleeve t-shirts. How would I get the total cost for that?
Well, short sleeve t-shirts are $5. They cost $5.
Mm-hmm.
So could you just do 10 times 550?
Okay. And then,
Long sleeve.
mm-hmm.
Bought 10 of them, you said?
I
2?
sure.
So $70 then?
Okay. So what we're going to do then is we're going to have 5 times the, well, maybe let's write it this way. We'll say cost of short sleeve. I'm going to just put short there. Times number of short sleeve plus cost. It's running out of space. Cost short sleeve times number short sleeve plus cost long sleeve times the number long sleeves. Everybody buy that? And then if I wanted the revenue, what am I going to do here? Really the same thing, right? It's the price of a short sleeve times the number of short sleeves plus the price of a long sleeve times the number of long sleeves. Does everybody kind of see that? So if we put all our numbers in then, it's 5s plus 7l equals 2,500. And then I have 8s plus 12l equals 4,200. That all look okay to you guys? Let's solve this via elimination because, again, we've noticed with elimination we can kind of avoid fractions. If we tried to do this by substitution, you're going to have a lot of fractions rolling around. It's okay with you guys? If I look at the variables s and l, it doesn't appear that one of them is really any easier to eliminate than the other. So let's say, for the sake of argument, let's eliminate the s's. What should I multiply equation A by and then equation B by so that the coefficients would become opposites? I should multiply equation A by 8, okay? And equation B by?
5.
Very close.
It's not 5? -5?
Yeah, one of them needs to be negative. It doesn't matter which one, but they need to be opposites. So one of the two needs to be negative. Let's make the 5 negative. So when I do multiply the first equation by 8, 8 times 5 is 40. 8 times 7 is 56. 8 times 2,500 is 20,000. Negative 5 times 8 is negative 40. negative 5 times 12 is negative 60, and negative 5 times 4,200 is negative 22,000. So when I add these down, I have negative 4L equals negative 2,000. So when I divide both sides by negative 4, I get 500. No. Where did I goof that? Let me just double check my arithmetic real quick. I did all that multiplying in my head, and now I'm second guessing myself. Ah, there we go. 21. So L is 250. Yes.
Where'd you get that 20,000?
8 times 2,500 is 20,000. Is that okay?
Yeah, I got it.
Okay. But were we looking for the number of long sleeve shirts? No, we want the number of short sleeves. So we'll just go ahead and plug that back into either equation. So when I divide both sides by 5, I get S is 150. Worth pointing out to you that we kind of did this the dumb way, that we would have been better off eliminating the L's to start, because then we would have gotten our answer for S right away. We wouldn't have had to back substitute. Not that that was that big of a deal, that little extra step, but we did do something dumb, which is fine, you know, not a big deal. This feels like a good place to stop for today. You guys happy with that? So at this point, you guys should be able to do 9 through 18 from the problem set. And at this junction, we finished, there's 4 sections in here, we finished 3 of them. I would expect a homework quiz here in the next class or 2, covering at least the first 2 sections. Cool with that?
Next class or 2 classes?
Here in the next class or 2, on at least the first 2 sections. Whoa! It's okay. You're falling. I don't think sometimes dreams even have that logic, right? It could just be like something else was happening. Oh, I'm falling. You know, who knows? Yeah, so that's that. Everybody happy?